Welcome, dear listener. You've found your way to Dreams of Gravity, and we're so glad you're here. Whether you've been here before or this is your very first time, know that this is a safe and quiet place, a place built just for moments like this one. Before we begin, take a moment for yourself. If you haven't already, find a comfortable position. Maybe you're already lying down, your head resting against a pillow, your blanket pulled close. Let your shoulders drop, unclench your jaw, let your hands go soft. Feel the weight of your body against whatever surface is holding you right now. That gentle, constant pressure is gravity. The same force that holds the moon in its orbit around the Earth, that keeps the Earth circling the sun, that pulls galaxies together across millions of light years. That same force is holding you right now, quietly and faithfully, to this planet. You don't have to do anything right now. You don't have to think about tomorrow or yesterday or anything that's waiting for you outside this moment. Right now, the only thing that exists is this voice and the quiet dark, and the vast and ancient universe stretching out in every direction around you. Take one slow breath in through your nose and let it out gently through your mouth. Good. Notice how natural that is. Your body knows exactly what to do. It has been breathing for every moment of your life without needing instruction, without needing effort. Just like the tides, just like the seasons, just like the orbit of the Earth, your breath follows a rhythm older than thought. We're going to take a long, slow journey tonight, out past the edges of what we know, through the deep oceans of space, through time itself. And somewhere along the way, you'll drift. And that's exactly what's supposed to happen. Tonight's story begins close to home, right here in our own solar system, with a small, distant, icy world that was once called the ninth planet of the Sun. A world that spent decades sitting quietly at the far edge of everything we knew, orbiting in the dark, largely unknown, largely unseen. And then, one day, scientists looked at it more carefully and quietly, carefully, changed the rules. This is the story of Pluto, and it is, in the gentlest and most beautiful way, a story about what it means to belong and what it means to let go. But before we get to Pluto, we need to start somewhere else. We need to start with the whole picture, because Pluto's story only makes sense when you understand the size and shape of the place it lives in. And that place, our solar system, our galaxy, our universe, is almost impossibly, breathtakingly vast. Close your eyes for a moment, if they aren't already closed. Imagine you are floating. Not falling, just floating, gently, the way you might drift in warm water on a summer afternoon. The surface is somewhere below you, and the sky is above, and you are perfectly suspended between them, weightless and still. The water is warm. The light that reaches you through the surface is soft and scattered and golden, and it moves in slow, shifting patterns above your face. There is no urgency here, no direction you need to swim. You are simply held. That feeling, that soft suspension, is a little bit like what it feels like to think about space. You're not falling into it, you're simply floating inside it, because you already are. Right now, as you lie here, the Earth beneath you is moving. It's spinning slowly on its axis, one full turn every 24 hours. And at the same time, it's orbiting the Sun at a speed of roughly 30 kilometers per second. That's about 107,000 kilometers per hour. And yet, you feel nothing. The motion is so smooth, so constant, so perfectly balanced that your body registers none of it. You simply rest, you float, and the Earth carries you silently and faithfully through the dark. By the way, I wonder, where are you watching from tonight? Which city and what time of day is it for you right now? Are you in a quiet apartment with the windows dark, or somewhere where a little light still filters through the curtains? I ask only because it's a beautiful thing to imagine. All the different places in the world where someone right now is lying down, pulling a blanket close and looking up at the same sky. We're spread so far apart, and yet here we are, together, in this moment. That's something worth appreciating. And now, let's go further out. The Sun is the heart of our solar system, and like all hearts, it sets the rhythm for everything around it. It is a star, yes, but to say that doesn't quite do it justice. The Sun is a sphere of hot plasma, about 1.4 million kilometers in diameter. If you were to hollow it out and pour the Earth inside, you could fit roughly 1.3 million Earths within its volume. It is so large that the light it produces, the same light that warms your skin on a summer morning, takes about 8 minutes and 20 seconds to travel from its surface to you. 8 minutes. Light, moving at 300,000 kilometers per second, takes 8 minutes just to cross that distance. And yet, on the scale of the universe, the Sun is not large at all. It is an average-sized star, a modest, middle-aged, perfectly ordinary star, remarkable only in that it happens to be ours. The Sun has been burning for about 4.6 billion years, and it will burn for approximately another 5 billion. In the language of stellar physics, it is what we call a main sequence star, a star in the long, stable middle period of its life, converting hydrogen into helium through nuclear fusion in its core. Every second, the Sun fuses approximately 600 million tons of hydrogen into helium, every second. And in doing so, it converts about 4 million tons of matter directly into energy, pure energy, radiating outward in all directions at the speed of light. Some of that energy, after traveling 150 million kilometers, falls upon the leaves of a tree, or the surface of an ocean, or the closed eyelids of someone lying quietly in the dark, listening to a story about space. You have received the Sun's light today, even if you didn't go outside, even if the day was overcast and grey. Some of that ancient nuclear energy made its way to you, and now you are resting, carrying it in the warmth of your body as you prepare to sleep. Around this star, 8 planets trace their long elliptical paths. Closest in, Mercury, a small cratered world without an atmosphere where the days are longer than the years. The surface of Mercury experiences temperature swings of more than 600 degrees Celsius between its day side and night side, blistering heat under the sun, and then extreme cold the moment that sunlight goes away, with nothing in the air to hold the warmth. It is a world of extremes, of stark contrasts, of absolute silence, broken only by the occasional impact of a meteorite on its ancient, pockmarked surface. Then Venus, veiled in thick clouds of sulfuric acid, hotter than a kitchen oven left on for eternity. Venus is in many ways Earth's twin, similar in size, similar in composition, similar in distance from the Sun. And yet, something went catastrophically different there, billions of years ago. A runaway greenhouse effect turned it into a furnace. The surface temperature is about 465 degrees Celsius, hot enough to melt lead. The atmospheric pressure at the surface is 90 times that of Earth's, equivalent to being nearly a kilometer underwater. And the thick clouds that permanently cover the planet reflect sunlight so effectively that Venus is the brightest object in our night sky after the moon. Beautiful from a distance, impossible up close. Then Earth, our blue and white and green island, the only place in all of known space where water runs freely across the surface and life has found a foothold. Then Mars, rust red and quiet, with dust storms that can swallow the entire planet, and canyons so deep and wide they make Earth's Grand Canyon look like a small scratch in the ground. Mars has the largest volcano in the solar system. Olympus Mons, nearly 3 times the height of Mount Everest, so wide that if you stood at its base, the summit would be below the horizon. Mars also has the longest canyon system, Valles Marineris, a network of chasms stretching across nearly a quarter of the planet's circumference, as if the planet had cracked under some ancient stress and never quite healed. There is evidence on Mars of an ancient, warmer, wetter past. River valleys carved by flowing water, dried lake beds, mineral deposits that only form in the presence of liquid. Something changed on Mars a long time ago. The atmosphere thinned, the magnetic field weakened, the water evaporated or froze underground, and the planet became the cold, dry desert it is today. What it was before is one of the most tantalizing mysteries in planetary science. And whether anything ever lived there, in those ancient oceans and rivers, is a question we have not yet answered. Beyond Mars, there is a belt, a broad ring of rocky and metallic fragments left over from the early days of the solar system, a region called the asteroid belt. It is often imagined as a dense, dangerous field, something a spacecraft has to carefully navigate, dodging rocks left and right. In reality, it is mostly empty space, with the occasional rock drifting silently through the dark. But it marks a boundary. It marks the place where the inner solar system ends and the outer solar system begins. And the outer solar system is a different world entirely. Jupiter is the first thing you encounter as you cross that boundary, and it is staggering. Jupiter is the largest planet in our solar system, so large that all the other planets combined would still not equal its mass. It is a gas giant, a world with no solid surface, just layer upon layer of swirling gas and liquid and exotic compressed matter descending deeper and deeper toward a core that may, or may not, be solid. On its surface, or rather in its upper clouds, a storm has been raging for at least 350 years. We call it the Great Red Spot. It is a hurricane larger than the Earth itself, spinning slowly, endlessly, an ancient and patient whirlpool of wind and color. Jupiter also has a family, a large and varied family of moons. 80 confirmed moons, as of our current knowledge, ranging from tiny irregular rocks a few kilometers across to 4 large worlds that Galileo Galilei himself observed in 1610 with one of the first astronomical telescopes. Those 4, Io, Europa, Ganymede and Callisto, are called the Galilean moons, and they are worlds in their own right. Io is the most volcanically active body in the solar system, its surface constantly reshaped by eruptions fed by the tidal flexing of Jupiter's enormous gravity. Europa has a smooth, icy surface, covering what appears to be a global ocean of liquid water, kept liquid not by solar heat, but by the same tidal forces that drive Io's volcanoes. Somewhere beneath Europa's ice, In that dark and pressurized ocean, conditions may exist that could support microbial life. It is one of the most compelling places in the solar system for the search for life beyond Earth. Saturn is next, ringed, serene, and somehow the most dreamlike planet in the solar system. Its rings are not solid. They are made of billions upon billions of small particles, ice and rock and dust, each one orbiting Saturn at its own speed, spread across a disk nearly 300,000 kilometers wide, but only about 10 meters thick in some places. That thinness is extraordinary. If you shrank Saturn's ring system to the width of a sheet of paper, the paper would need to be roughly the size of a football field. And yet, when you look at Saturn through a telescope, the rings glow with a soft, luminous beauty, like the halo around a candle flame seen through fog. Saturn's largest moon, Titan, is one of the strangest and most fascinating worlds in the solar system. It is larger than the planet Mercury. It has a thick atmosphere, the only moon in the solar system with one worth mentioning, made mostly of nitrogen, with a surface pressure slightly higher than Earth's. On Titan's surface, there are rivers and lakes and seas, but not of water, of liquid methane. It rains methane on Titan. Methane rivers carve methane valleys into the icy bedrock. The temperature on Titan's surface is about minus 179 degrees Celsius, so cold that water ice acts like rock, and the only liquids are hydrocarbons. It is a world with weather and geology and seasons, but built from entirely different materials, following entirely different chemistry. A different version of a world. A reminder that the universe is more creative than our imaginations. Uranus and Neptune, the outermost of the recognized planets, are quieter and colder and bluer. Uranus is tilted so dramatically on its axis that it essentially rolls around the Sun on its side. The result, astronomers believe, of a massive collision early in the solar system's history. A collision so powerful it knocked the entire planet sideways and left it forever altered. Neptune is windier than any other planet. Its atmospheric winds blow at speeds of over 2,000 kilometers per hour, the fastest in the solar system, howling across a world where the average temperature is nearly minus 200 degrees Celsius. And then, beyond Neptune, the solar system doesn't simply end. It gets quieter, it gets colder. It spreads out into a vast, diffuse region of space called the Kuiper Belt. A wide band of icy objects, frozen remnants from the birth of the solar system, orbiting the Sun at great distances in the slow, patient dark. And it is here, in this quiet outer wilderness, that Pluto has always lived. Pluto was discovered in 1930 by a young American astronomer named Clyde Tombaugh. He was 24 years old, working at the Lowell Observatory in Arizona, carefully comparing photographic plates of the night sky, images taken days apart, looking for any object that had shifted position. Stars don't move, or rather, they move so slowly that over the course of a few days they appear fixed. But a planet, or a large body orbiting the Sun, would move. It would drift ever so slightly between one photograph and the next. And that is exactly what Tombaugh found. A tiny point of light drifting slowly against the background of stars. They named it Pluto, after the Roman god of the underworld, fitting, perhaps, for something so distant and so cold and so dark. The name was suggested by an 11-year-old girl in Oxford, England. Venetia Burney, sitting at the breakfast table one morning in March of 1930, reading the newspaper with her grandfather about the newly discovered world. She suggested Pluto, the god of the dark underworld, because it seemed right for something so far from the sun, so cold, so hidden. Her grandfather passed the suggestion along through his connections to the Lowell Observatory, and it was adopted. An 11-year-old girl gave a world its name, and that name carried for 76 years. For those 76 years, Pluto was considered the 9th planet of the solar system. It appeared in textbooks. It was included in models and charts and children's drawings of the solar system. It was ours. And most people, scientists included, didn't think too hard about what exactly it was. It was simply a planet. Small, yes, smaller than Earth's moon, in fact, but a planet nonetheless. And then things began to change. As telescopes improved and our ability to scan the outer solar system grew more sophisticated, astronomers began finding things. Not just Pluto, but other objects, many other objects, orbiting the Sun in that same distant region beyond Neptune. In 2002, a large object was found and named Quaoar. In 2004, another called Sedna. And then, in 2005, came the discovery that would force everything to change. A team of astronomers led by Mike Brown, who would later jokingly call himself the man who killed Pluto, discovered an object in the outer solar system that appeared to be larger than Pluto. They named it Eris. Eris changed everything, because now astronomers had a problem. If Pluto was a planet, then Eris was a planet too. And if Eris was a planet, then Quaoar probably was, and Sedna probably was, and so were dozens, perhaps hundreds, of other similar objects that were being found and catalogued in the Kuiper Belt. The solar system could not have 9 planets. It would need 50, or 100, or more, as better telescopes revealed more and more of the distant, frozen dark. So the International Astronomical Union, the body responsible for defining and naming things in the sky, convened a meeting in Prague in August of 2006. And after considerable debate, they did something that made headlines around the world. They created a formal definition of the word planet. And under that definition, Pluto did not qualify. To be a planet under the new rules, a body must do 3 things. It must orbit the Sun. Pluto does this. It must have enough mass for its own gravity to pull it into a roughly spherical shape. Pluto does this too. But the third requirement is the one Pluto fails. A planet must have cleared the neighborhood around its orbit, meaning it must be gravitationally dominant in its region of space, having either absorbed or ejected other objects that share its orbital path. And Pluto, small as it is, orbiting within the crowded Kuiper Belt, surrounded by countless other icy bodies, has not done this. It never could. There are simply too many other objects in its neighborhood, and Pluto is too small to dominate them. And so, in 2006, Pluto was reclassified. Not deleted, not erased, but gently, carefully moved into a new category. A category created specifically to accommodate it and the other objects like it. That category is called a dwarf planet, and Pluto became the most famous dwarf planet in the solar system. The response from the public was immediate and emotional. People were upset. Many astronomers were upset too. The vote was not unanimous, and the debate about the definition of planet continues to this day in some scientific circles. Children wrote letters. Petitions were signed. Save Pluto bumper stickers appeared on cars. There was a mourning that surprised many people. A genuine, heartfelt mourning for a small icy world at the edge of the solar system that most people had never seen and never would. Why did it matter so much? Perhaps because Pluto had been part of our picture of the solar system for so long. Perhaps because we had given it a name, a personality almost, and because our names for things carry weight. To name something is to claim it, to include it, to say that this thing belongs. And when you take that name away or change what it means, there is a small grief in it, a small sense of loss. It is the same feeling, perhaps, as when a word you've always known turns out to be spelled differently than you thought. A small crack in the familiar. A reminder that the maps we draw of the world are not the world itself. But here is what I find beautiful about Pluto's story. And here is why I think it's worth telling slowly on a quiet night like this one. Pluto didn't change. Not one atom of it moved. The reclassification happened entirely in human minds, in the language we use to describe the universe, not in the universe itself. Pluto is still there right now as you lie here in the dark. It is still making its long, slow, 248-year orbit around the Sun. It has 5 moons, Charon being the largest, so large relative to Pluto that some astronomers consider them a double dwarf planet, 2 worlds orbiting each other as they orbit the Sun. It has a thin atmosphere of nitrogen and methane that freezes and falls to the ground as the planet moves away from the Sun, and then sublimates and rises again as it draws closer. It has mountains made of water ice rising 3 kilometers above plains of frozen nitrogen. It has a heart. That last part is literally true. When NASA's New Horizons spacecraft flew past Pluto in July of 2015, after a 9.5-year journey of 5 billion kilometers, it sent back images that stunned the world. And among the first things visible on Pluto's surface was a vast, pale, heart-shaped region of frozen nitrogen, smooth and bright and ethereal against the darker, more rugged terrain around it. Scientists named it Tombaugh Regio, in honor of the man who discovered Pluto. But most people simply called it the heart. Pluto has a heart, and perhaps that's enough. Think about that for a moment as you let your body relax a little more deeply. A world at the very edge of the solar system. A world so cold that nitrogen itself freezes solid on its surface. And it has a heart. Not because it is alive, not because it feels anything, but because the universe, in its slow and ancient way, shaped the ice and rock and light into something that, from a distance of 5 billion kilometers, looked to our eyes like a heart. Sometimes the universe is simply beautiful in ways we didn't ask for and didn't expect. New Horizons changed everything we knew about Pluto. Before the flyby, Pluto was a blurry smudge, even in the best images from the Hubble Space Telescope. We knew almost nothing about what it actually looked like up close. And then, in the space of a few hours, as the spacecraft swept past at over 50,000 kilometers per hour, we received images of extraordinary clarity and detail. Mountains, valleys, vast smooth plains of ice, a sky with hazes and layers of blue-tinted atmosphere, and that extraordinary heart. It was a reminder that every world in the solar system, even the smallest, most distant, most forgotten, is a complete and complex place. A world with geography and weather and history and beauty. We tend to think of the outer solar system as empty, cold, lifeless, and in many ways it is. But empty does not mean featureless, and cold does not mean simple. Every object out there, from the largest gas giant to the smallest icy fragment drifting through the Kuiper Belt, is a record of the solar system's history. A fossil, in a sense, preserved by the cold. The icy bodies of the outer solar system are time capsules, fragments of the original material from which the solar system was built, preserved in deep cold for billions of years. When we study them, we are reading the diary of our origins. Now, let's pull back. Let's float up and away from Pluto, away from Neptune and Uranus and Saturn and Jupiter and Mars, and the asteroid belt and Venus and Mercury and Earth. Let's float up and out until the entire solar system is just a small bright smudge in the dark. And then, let's keep going. Beyond the Kuiper Belt, the solar system extends even further, into a region called the Oort cloud. The Oort cloud is not a cloud in any sense that we usually mean. It is an enormous, roughly spherical shell of icy objects surrounding the solar system at a distance of perhaps 100,000 astronomical units. 1 astronomical unit being the distance from the Earth to the Sun. The outer edge of the Oort cloud may extend nearly a quarter of the way to the nearest star. It is, in a very real sense, the outermost boundary of the solar system, the point at which the Sun's gravitational influence finally fades into the broader gravitational field of the galaxy. We have never directly observed the Oort cloud. We infer its existence from the behavior of long-period comets. Comets that have very long orbital periods, sometimes hundreds of thousands of years, that seem to originate from all directions, rather than from the flat plane of the solar system. These comets, astronomers believe, are objects from the Oort cloud that have been nudged by a passing star or some other gravitational disturbance, sending them on long, slow journeys inward toward the Sun. Some of them have been traveling for millions of years before they ever come close enough for us to see. A comet's journey inward is one of the most beautiful and ancient events in the solar system. An object of rock and ice formed in the cold outer dark billions of years ago, disturbed from its long stillness by some ancient event, and slowly drawn inward toward the warmth of the Sun. As it approaches, the Sun's radiation heats the ice on its surface, turning it directly from solid to gas, a process called sublimation, and the gas and dust stream away to form the comet's famous tail. The tail always points away from the Sun, driven outward by the solar wind, regardless of which direction the comet is traveling. A comet's tail is not a trail. It is not where the comet has been. It is where it is going. There is something deeply meditative about that image. A comet, ancient and cold, falling toward the light, its tail streaming out ahead of it, pointing the way, moving through space in perfect silence, leaving nothing behind. Now let's go further, much further. The nearest star to our Sun is a small red dwarf called Proxima Centauri, part of a triple star system called Alpha Centauri. It is 4.24 light-years away. A light-year is the distance light travels in 1 year, about 9.46 trillion kilometers. Proxima Centauri is, therefore, roughly 40 trillion kilometers away. Our fastest spacecraft, New Horizons, which is currently moving away from the Sun at about 14 kilometers per second, would take approximately 78,000 years to reach it. Let that settle for a moment. The closest star, the closest Sun-like object to our own, 78,000 years away at the speed of our fastest machine. And yet, Proxima Centauri is not nothing. It has at least one confirmed planet, Proxima b, orbiting within what scientists call the habitable zone, the range of distances from a star where liquid water could exist on the surface of a planet with the right atmosphere. Proxima b is a roughly Earth-sized world, orbiting its star every 11 days. Whether it actually has an atmosphere, whether it has water, whether it has anything resembling the conditions for life, we don't know. But it is there, just over 4 light-years away, orbiting the closest star to our Sun. The universe does not make us wait long, at least by cosmic standards, before offering another world to wonder about. The universe does not care about our sense of distance or time. It is under no obligation to be conveniently sized. The distances between stars are not merely large, they are incomprehensible in the most literal sense. Our minds did not evolve to understand scales this vast. We can say the numbers, we can do the mathematics, but to truly feel 40 trillion kilometers is not something human consciousness was built for. And perhaps that is okay. Perhaps there is something freeing about that. Some things are so large that you can only surrender to them. You can only float. Within our galaxy, the Milky Way, there are somewhere between 100 billion and 400 billion stars. Each one is a sun. Many of them have planets. Some of those planets, in all likelihood, have conditions that could support life. We have not confirmed this. We have not yet found life beyond Earth. But the mathematics of probability, combined with what we know about chemistry and the prevalence of the conditions for life, makes it difficult to believe that Earth is alone. Not certain, difficult to believe. The Milky Way itself is a barred spiral galaxy, a flat spinning disk of stars, gas and dust, with a bright central bar and spiral arms curving out from it. Our Sun sits in one of those spiral arms, about 26,000 light-years from the galactic center. The entire galaxy is about 100,000 light-years across. If you were able to look down at it from above, you would see something like a slow, luminous whirlpool. A pinwheel of light turning in the dark, billions of stars caught in a graceful rotation, each one following the invisible curves of gravity like leaves on a slow river. The Milky Way completes one full rotation every 225 to 250 million years, a period sometimes called a cosmic year or a galactic year. Our solar system has completed about 20 of these orbits since it formed. In the time it took the Earth to travel once around the galactic center, entire species appeared and went extinct here on the surface. The dinosaurs lived and vanished within a fraction of a single galactic year. Our entire recorded human history, every empire, every war, every invention, every story ever told, occupies a vanishingly small sliver of a single cosmic rotation. We are passengers on a very old, very slow wheel, and the wheel turns regardless of what happens on its surface. At the very center of the Milky Way, and at the center of most large galaxies, there is something extraordinary, a supermassive black hole. In our galaxy, it is called Sagittarius A star, and it has a mass of about 4 million times that of our Sun. It sits at the center of the galaxy, quiet and invisible. Invisible because black holes do not emit light. They swallow it. Their gravity is so intense that nothing, not even photons, the particles of light, can escape once they cross the event horizon, that invisible boundary beyond which return is impossible. In 2019, astronomers released the first ever direct image of a black hole. Not Sagittarius A star itself, but the supermassive black hole at the center of a galaxy called M87, about 55 million light-years away. The image showed a glowing ring of hot gas surrounding a dark central region, the shadow of the black hole itself, where light bends so severely around the event horizon that it traces a bright, luminous circle before some of it falls in forever. It was one of the most remarkable scientific achievements of the modern era. A global network of radio telescopes working in coordination across multiple continents, effectively turning the entire Earth into a single enormous telescope, all focused on a single point in the sky. And what they saw was exactly what Einstein's equations had predicted a century earlier. A black hole is perhaps the most extreme object in the universe, a place where the laws of physics as we understand them break down, where space and time are so warped by gravity that they lose the familiar shape and behavior we experience in our everyday lives. Near a black hole, time itself slows down. If you were to hover at a safe distance above the event horizon of a large black hole and then descend very slowly toward it, you would notice, or rather, you would not notice because it would happen gradually, that time was passing more slowly for you than for someone watching from far away. This is not a metaphor or a thought experiment. It is a real, measured, experimentally confirmed effect predicted by Einstein's theory of general relativity. Time is not fixed. It is not the same everywhere. It bends and stretches under the influence of gravity, like a fabric pulled and distorted by weight. We think of time as a constant, a steady river flowing from past to future at the same rate for everyone. But it isn't. Two identical atomic clocks, synchronized perfectly, will read different times if one is placed on a mountaintop and the other at sea level. Because at sea level, the Earth's gravity is slightly stronger and time runs slightly slower. The difference is infinitesimally small, nanoseconds, but it is real. GPS satellites in orbit have to account for this effect in their calculations. If they didn't, GPS systems would accumulate errors of several kilometers per day. Time is flexible, and near a black hole, that flexibility becomes extreme. Imagine, for a moment, standing at the edge of a great dark ocean. The water is perfectly still. You can see nothing beneath the surface. You know that somewhere, far below, there is something vast and ancient, something that the water is slowly, imperceptibly drawn toward. You are standing at the shoreline, and the shore itself is the event horizon, the boundary beyond which the current is too strong, beyond which even light cannot swim back to the surface. Beyond that shore, everything that enters is gone. Not destroyed, perhaps. The physics of what happens inside a black hole is something we genuinely don't know because we have no way to observe it, and our equations stop working there. But gone, from our perspective, gone forever. That image, the dark ocean, the invisible current, the shore that nothing crosses back from, is one of the gentlest ways I know to think about a black hole. Not as a monster or a destroyer, but as a deep mystery, a place the universe keeps to itself. Black holes are born from death. When a very massive star, much larger than our Sun, reaches the end of its life and exhausts its nuclear fuel, it can no longer sustain the outward pressure of the nuclear reactions in its core. Gravity wins. The core collapses inward with extraordinary speed, and the outer layers of the star fall inward and then bounce back outward in a catastrophic explosion called a supernova. A supernova releases more energy in a few seconds than our Sun will release in its entire 10 billion year lifetime. They are among the brightest events in the universe. A single supernova can briefly outshine an entire galaxy of 100 billion stars. If the collapsing core is massive enough, it continues to collapse beyond the point where any known force can stop it, until the density becomes infinite and a black hole is formed. If the core is somewhat less massive, it becomes a neutron star, an extraordinarily dense sphere of neutrons, roughly the size of a city, but with a mass greater than that of our Sun, rotating at speeds of hundreds of revolutions per second, sometimes emitting regular pulses of radio waves as it spins, which is why they are sometimes called pulsars. A teaspoon of neutron star material would weigh roughly 4 billion tons on Earth. And the material ejected in a supernova doesn't disappear. It drifts outward into space, slowly expanding, cooling, forming clouds of gas and dust called nebulae. And over millions of years, these clouds of expelled stellar material become the nurseries for new stars. New stars, born from the remains of old ones. The carbon in your body, the iron in your blood, the calcium in your bones. All of it was forged in the hearts of stars that lived and died before our Sun was born. You are, in the most literal sense, made of starlight, made of ancient stellar explosions. The atoms that compose you have been part of stars, of nebulae, of planets, of oceans, of other living things, over billions of years. You are not separate from the universe. You are a part of it, a temporarily organized, briefly conscious part of an ongoing cosmic process. Let that thought sit with you as you breathe slowly, in and out. The same atoms that have traveled across billions of years and billions of kilometers are, right now, cycling in and out of your lungs with every breath. The air you breathe has been breathed by ancient creatures. The iron in your blood came from a dying star. You are extraordinarily old in the most fundamental sense, even as you are extraordinarily new. The universe itself is approximately 13.8 billion years old. We know this with remarkable precision through a combination of methods. Studying the cosmic microwave background radiation, which is essentially the afterglow of the Big Bang, still faintly detectable everywhere in the universe today. Measuring the expansion rate of the universe to calculate how long ago everything was in the same place, and studying the oldest stars, whose ages can be inferred from their compositions and the physics of stellar evolution. The Big Bang was not an explosion in space. This is a common and understandable misunderstanding. It was, rather, an expansion of space itself. Before the Big Bang, or more precisely, at and immediately after the Big Bang, space and time did not exist in any form we would recognize. The entire observable universe was compressed into a point of almost infinite density and temperature, and then began to expand. Space itself stretched. The matter and energy within it spread outward. And over billions of years, as the universe expanded and cooled, atoms formed, then clouds of gas, then the first stars, then galaxies, then planets, then, eventually, life. Those first stars were extraordinary objects. They are known to astronomers as population 3 stars, and none of them exist anymore. They all burned out and died billions of years ago. They were made almost entirely of hydrogen and helium, the only elements that existed in the early universe. They were likely enormous, perhaps hundreds of times more massive than our Sun. and they burned brilliantly but briefly, exhausting their fuel in just a few million years. When they died, they seeded the universe with heavier elements: carbon, oxygen, nitrogen, iron, the building blocks of planets and chemistry and life. We are made of those first stars too. Every generation of stars enriched the universe a little more, added more complexity to the periodic table, made possible a little more of the extraordinary variety we see around us today. We are very late arrivals in cosmic terms. Our Sun was born about 4.6 billion years ago, roughly a third of the way through the universe's current age. Earth formed around the same time. The first life on Earth appeared perhaps 3.8 to 4 billion years ago. Complex multicellular life, animals and plants as we would recognize them, is a much more recent development, appearing in the last few 100 million years. And human beings, our species, Homo sapiens, have been here for perhaps 300,000 years. On the cosmic timeline, if the universe's entire history were compressed into a single year, humans would appear in the last few seconds of the last hour of December 31st. We are extraordinarily new, and yet here we are, thinking, wondering, lying awake at night and looking up at the stars and asking where all of this came from and what it means. The universe as a whole contains an estimated 2 trillion galaxies. 2 trillion. Each one containing hundreds of billions of stars. The scale of it is not something that should make you feel small, or rather, if it does, let it also make you feel magnificent. You are a part of something so vast and so ancient that no human mind can fully contain it. And yet you are here, inside it, sensing it, thinking about it. That is extraordinary. Let's return for a moment to the galaxies themselves. They come in extraordinary varieties. Spiral galaxies like the Milky Way, with their graceful arms. Elliptical galaxies, large, smooth, oval-shaped collections of older stars, without the active star formation happening in spirals. Irregular galaxies, which don't fit neatly into either category, their shapes disrupted by gravitational interactions with neighbors. And lenticular galaxies, something between spiral and elliptical, like a spiral that has used up most of its gas and slowed its star formation, retaining the disk but losing the arms. Galaxies are not isolated. They cluster together under the influence of gravity. Our Milky Way is part of a small cluster called the Local Group, which contains about 50 galaxies, including our nearest large neighbor, the Andromeda Galaxy, which is about 2.5 million light-years away. The light you see from Andromeda, if you've ever spotted it on a clear, dark night as a faint smudge in the constellation Andromeda, left that galaxy 2.5 million years ago. You are looking back in time. The Andromeda you see is the Andromeda of 2.5 million years ago. The universe has no single now. Every direction you look is a different moment in time, and Andromeda is coming toward us. Unlike most galaxies, which are moving away from us as the universe expands, Andromeda and the Milky Way are gravitationally bound to each other, and they are slowly closing the distance. In about 4.5 billion years, they will collide, or rather, merge. The two galaxies will pass through each other, their stars mostly missing one another because of the vast distances between individual stars, but their gas and dust clouds colliding and triggering enormous bursts of new star formation. Over billions of years, the two galaxies will merge into a single large elliptical galaxy. Astronomers have already given it a name, Milkomeda, Our Sun will likely survive this merger, though its position within the new galaxy will be changed. If Earth is still here, which depends on many things, including whether the Sun has expanded into a red giant and swallowed the inner planets by then, the night sky over Earth during and after the merger would look extraordinary. Instead of a single band of light across the sky, as the Milky Way appears to us now, there would be a bright, complex tangle of light in every direction, the combined stars of two galaxies slowly becoming one. That is one of the things I find most beautiful about astronomy. It doesn't just tell you about the past, it tells you about the future. Not the future of human civilizations. That's too far downstream, too uncertain. But the future of the universe itself. We can calculate with reasonable confidence what the night sky will look like 4 billion years from now. We can describe the death of our Sun. We can trace the eventual fate of the cosmos. That is an extraordinary gift of understanding. Our Sun, like all stars, has a limited lifespan. It is currently about halfway through its main sequence, the stable period of its life when it is burning hydrogen into helium in its core, generating the energy and light that sustain all life on Earth. In another 5 billion years or so, the Sun will exhaust the hydrogen in its core and begin to expand. It will grow slowly but relentlessly, swelling outward as the balance between gravity and radiation pressure shifts. It will become what astronomers call a red giant. As it expands, it will first swallow Mercury, then Venus, and possibly Earth as well, though the details depend on how much mass the Sun loses as it expands, which affects how far the planets orbit outward in response. After the red giant phase, the outer layers of the Sun will be expelled gently into space, forming a beautiful expanding shell of glowing gas, a planetary nebula. The term is misleading. Planetary nebulae have nothing to do with planets. They were named by early astronomers who thought they looked a little like planets through small telescopes. What they actually are is the outer envelope of a dying star, illuminated by the hot core left behind. And that core, the remnant of the Sun's core, stripped of its outer layers, will cool and condense into a white dwarf. A white dwarf is a dense, hot sphere about the size of the Earth, composed mostly of carbon and oxygen, slowly cooling over billions of years. It no longer generates energy through nuclear fusion. That process has ended. It simply radiates the heat it already has, growing dimmer and cooler as the ages pass. Over trillions of years, a white dwarf cools into something called a black dwarf, a cold, dark, inert sphere drifting silently in space. No light, no heat, just mass, quietly occupying its corner of the universe. We believe no black dwarfs yet exist. The universe is not old enough. The cooling process takes longer than the current age of the cosmos. Every white dwarf that has ever formed is still glowing. In some distant future, they will all go dark one by one as the last light of the last stars fades from the universe. Let's slow down here in this quiet passage of thought. The universe is not infinite in time. It is very, very old. 13.8 billion years, and it may last for an almost unimaginably longer time. But it is not eternal. On long enough timescales, even stars burn out. Galaxies go dark. Black holes, which might seem permanent, slowly lose mass over enormous spans of time through a quantum mechanical process called Hawking radiation, named for Stephen Hawking, who predicted it theoretically in 1974. A stellar mass black hole might take 10 to the power of 67 years to evaporate completely through Hawking radiation. A supermassive black hole might take 10 to the power of 100 years or more. These are numbers so large they have no intuitive meaning. They make the current age of the universe look like a fraction of a second in comparison. And yet, eventually, even the black holes will be gone. What remains after that? Theoretical physics suggests that the very last stable particles, protons perhaps, may also decay given enough time. The universe may end in a state of maximum entropy, a cold, dark, uniform void in which nothing happens and nothing changes, because there is no longer any difference in energy from one place to another. This hypothetical end state is sometimes called the heat death of the universe. Not a bang, not a collapse, just stillness. Permanent, perfect stillness. But we are very, very far from that. Right now, the universe is young and bright and busy. Stars are being born right now in nebulae scattered across the galaxy. Planets are forming around those stars. In some cases, perhaps, the chemical reactions that lead to life are beginning. The universe is alive with process and change and light. And somewhere in all of that, in the vast, spinning, expanding, ancient, luminous universe, there is this small blue planet, tilted slightly on its axis, orbiting a modest yellow star, accompanied by one large moon that keeps its oceans gently stirred and its seasons regular. A planet covered in water and cloud and the soft green and brown of land. A planet where, for reasons that still astonish scientists, the laws of chemistry and thermodynamics organized themselves into structures capable of self-replication, adaptation, memory, thought, wonder. We don't know how common this is. We don't know whether life exists elsewhere. We don't know whether, somewhere out there, a being is looking up at its own sky and asking the same questions we ask. But we know that it happened here. We know that the universe made us, made these minds, these hearts, these questions, at least once. And once is already extraordinary. There is another thing worth knowing, a quiet, humbling fact that astronomers sometimes call the overview effect, named for the experience reported by astronauts when they first see the Earth from space. From orbit, or from the Moon, or from the window of a spacecraft heading to Mars, the Earth looks small. Not insignificant. Beautiful. Deeply beautiful. More beautiful than any photograph can capture. But small. A marble in the dark. A pale blue dot, as Carl Sagan famously described it, suspended in a sunbeam. And something about seeing that tends to dissolve, at least temporarily, the feeling that any particular conflict or division on its surface matters very much. The borders we draw, the categories we insist upon, planet or dwarf planet, this country or that one, this group or that group, all of it is a small conversation happening on the surface of a small world in a large and patient universe. That is not a reason to stop caring. Quite the opposite. It is a reason to care more carefully, more gently, more wisely. The Earth is small. What happens on it matters precisely because it is small and rare, and the only home we have. The overview effect doesn't produce indifference. It produces tenderness. And it made Pluto too. That small, icy, heart-shaped world at the edge of everything. Still there. Still orbiting. Still carrying the gentle memory of the man who found it, written in frozen nitrogen on its surface. Still turning, slowly and quietly, in the cold outer dark. We gave Pluto a name, and then we changed what that name meant. But Pluto didn't notice. It didn't need our categories. It was what it always was. A world, old and cold and beautiful, doing what it had always done, on a schedule so slow that a single orbit takes longer than all of recorded human history. Maybe that's one of the things that space teaches us, if we let it. That our categories, our definitions of what belongs and what doesn't, what counts and what doesn't, are human inventions, useful, sometimes necessary, but ultimately separate from the thing itself. The universe doesn't classify, it simply is, and everything in it, every planet and dwarf planet and asteroid and comet and star and black hole and drifting atom of hydrogen in the cold space between galaxies, simply is as well. Each one doing exactly what it must, following the mathematics of gravity and chemistry and thermodynamics with perfect, patient fidelity. There is something restful about that, something deeply calming in the recognition that out there, in the vast dark, the laws of physics are holding everything together. The stars will burn for billions of years without needing to be told. The planets will orbit without needing to be reminded. The comets will fall inward when their time comes, trailing their backward-pointing tails, and the nebulae will slowly contract under gravity and birth new stars, and the galaxies will continue their stately rotation, and none of it requires our attention, our worry, our effort. You can let go. You can rest. The universe has been doing this for 13.8 billion years without any help from us, and it will do it for billions more. Your small piece of it, this body, this breath, this quiet room, is safe in the embrace of the Earth, which is safe in the embrace of the Sun's gravity, which is safe in the slow rotation of the Milky Way, which is drifting through the local group, which is drifting through the Virgo supercluster, which is caught in the slow tide of the observable universe's expansion. Everything is moving. Everything is held. And right now, for you, there is nothing to do but rest. Let your breathing slow a little more. In through the nose, gently, and out through the mouth, slowly. Again. You don't have to do anything with that breath. Just let it happen. Your body knows how to breathe. It's been doing it since before you were aware of anything. Just like the stars, just like the planets orbiting in the dark, your body knows its work, and it does it without effort. Think of the space between stars. Not the stars themselves, with their fire and pressure and nuclear heat, but the space between them. The quiet, cold, nearly empty space that makes up most of the volume of the universe. It is not truly empty. There are stray atoms of hydrogen, the occasional dust grain, the background radiation of the Big Bang still faintly humming everywhere. But it is very, very quiet, very still. If you could somehow be transported there, outside any solar system, far from any star, you would find a stillness beyond anything you have ever experienced. The darkness would be absolute. Not the soft dark of a closed room, but a darkness without any nearby source of light. The silence would be total. Sound cannot travel through the vacuum of space. And the cold would be extreme. The temperature of deep space, far from any star, is about minus 270 degrees Celsius, close to absolute zero. And yet, in that stillness, in that dark and cold and silence, the universe is full of structure, full of the invisible lines of gravity connecting everything to everything else, full of the faint background glow of billions of years of history, full of photons traveling in all directions, carrying the light of ancient events. Supernovae that exploded before Earth existed, quasars that burned at the dawn of the universe, galaxies so far away their light has been traveling for more than 13 billion years. The universe is full of messages. We just need to know how to read them. Astronomers do this with every tool they have, not just visible light telescopes, which can only see the same narrow band of the electromagnetic spectrum that our eyes can detect, but radio telescopes, which detect radio waves, infrared telescopes, which detect heat, X-ray telescopes, which detect high-energy radiation from extreme events, gamma-ray observatories, gravitational wave detectors. Each instrument reveals a different layer of the universe, a different frequency of its speech. And together they build a picture, incomplete, always incomplete, but richer with each passing year. In 2015, for the first time, we detected gravitational waves, ripples in the fabric of space-time itself, predicted by Einstein in 1916, but not confirmed until nearly a century later. The first detection was caused by two black holes, each about 30 times the mass of our Sun, spiraling together and merging in a distant galaxy about 1.3 billion light-years away. The merger released more energy in a fraction of a second than the entire Milky Way galaxy emits in that same fraction of a second. Almost all of it in the form of gravitational waves. And those waves spread outward through space at the speed of light, stretching and compressing the very fabric of space as they traveled. And after 1.3 billion years of traveling, they reached Earth and caused the two enormous L-shaped detectors of the LIGO Observatory to vibrate by a distance smaller than 1/10,000th the diameter of a proton. And we heard it. We heard the universe shake, just barely, by an almost incomprehensible amount. And we noticed. That is the miracle of science. Not just that the universe is extraordinary, but that we, with our small fragile minds and our instruments made of glass and metal and wire, have found ways to listen to it. There are things we don't yet understand. Many things. We know, for instance, that the universe contains far more matter than we can see. The visible matter, stars, gas, dust, planets, everything that emits or reflects light, accounts for only about 5% of the total energy content of the universe. About 27% is something we call dark matter, matter that has mass and interacts gravitationally, but does not emit, absorb, or reflect light. We cannot see it. We can only infer its presence from its gravitational effects on visible matter. The way galaxies rotate, the way light bends around galaxy clusters, the large-scale structure of the universe itself, all of these point clearly to the presence of something we cannot see, but cannot ignore. And the remaining 68% is something even more mysterious: dark energy, a property of space itself that appears to be driving the expansion of the universe to accelerate. We don't know what it is. We don't fully know how it works. We simply call it dark energy because we needed a name for the thing that the evidence told us must be there. And there is something comforting about that, about the fact that after all we've learned, all the satellites and telescopes and equations and observations, 95% of the universe remains not fully understood. Not because we're not looking, not because we're not smart enough, but because the universe is simply vast and deep and layered in ways that take time to unfold. We are 13.8 billion years into a journey that has no end in sight. We are still early. There is a particular kind of peace that comes from sitting with the unknown. Not the anxious unknown, not the uncertainty of tomorrow's news or next week's worries, but the vast, ancient, philosophical unknown. The kind that has always been there, that existed before humans did, and will remain long after. The kind that doesn't demand an answer tonight. The kind you can simply rest beside, the way you might rest beside a river without needing to know where it goes. The universe, in this sense, is the deepest unknown there is. And yet, it is also the most familiar. You have been inside it every moment of your life. You have never been anywhere else. Its rules govern your heartbeat and the arc of a thrown stone, and the color of the sky at sunset, and the reason the moon rises and sets. The unknown and the intimate are the same thing, seen from different distances. Let that thought carry you a little deeper towards sleep. You are inside the great mystery. You have always been, and you are safe inside it. There is one more thing I want to tell you about before you drift away completely. Something that I find endlessly beautiful and endlessly calming. It is about light. Every photon of light, every particle of light that has ever existed, has been traveling since the moment it was created. Light does not stop. It does not rest. It moves at 300,000 kilometers per second through the vacuum of space, and it keeps moving until it hits something. A planet, a telescope lens, a retina. And in the moment it hits that surface, it is absorbed, and its journey ends. In that ending is a kind of arrival, a completion. The light that falls on your closed eyelids right now, the faint ambient glow in your room, whatever it is, has been traveling to reach you. Some of it began its journey in a light bulb a few meters away, a fraction of a second ago. But some of the light that touched your face today, earlier, when you were outside or near a window, began its journey 8 minutes ago at the surface of the sun. And the sunlight that warmed the earth that grew the food that feeds you began its journey in the sun's core as a gamma ray produced by nuclear fusion roughly 100,000 years before it even reached the surface of the sun. It took that long to work its way through the dense, churning interior of the star, bouncing, absorbing, re-emitting, before finally escaping as visible light and racing across 150 million kilometers of space to reach you. Every interaction with light is an arrival. Every moment you see anything, something that has traveled an unimaginable distance, has finally found its destination. You are, in a very real sense, the destination of ancient journeys happening all the time, without pause, without effort, in every direction. And somewhere, right now, photons are leaving your body too. Infrared radiation, heat, radiates from your skin into the air, into the room, into the world. You are glowing, faintly in wavelengths the eye cannot see. You are emitting light. You are a small, warm, quietly radiant part of the universe's ongoing conversation with itself. Stars do this on a grander scale. A star is essentially a conversation between gravity and radiation. Gravity pulling inward, trying to collapse the star, and the outward pressure of nuclear radiation pushing back, trying to expand it. A star is a perfect, sustained negotiation between two enormous forces, a balance maintained for billions of years. And when the fuel runs out and the negotiation ends, the star changes form, becomes a white dwarf or a neutron star or a black hole, depending on its mass. And the light it was producing, that steady outward stream of photons, ceases. But even then, the last photons it ever produced are still traveling. They are still out there in space, moving at 300,000 kilometers per second, carrying the final light of a dead star. Some of the stars you see in the night sky are already dead. Their light is still reaching you, still arriving, still completing its journey. But the source is gone. What you see is a memory, a ghost of light from something that no longer exists. There is something quietly profound about that. Looking at the night sky is looking at the past, not metaphorically, literally. The light from a star 1,000 light years away left that star 1,000 years ago. What that star looks like right now, you cannot know. You can only see what it was. The night sky is a time machine in every direction, showing you layers of the past simultaneously. Some stars near and recent, others far and ancient. All of their lights arriving at your eyes at the same moment, as if the universe had arranged them all for you. A mosaic of different moments, a tapestry of time. And among all those stars, somewhere in the direction of the constellation Ophiuchus, if you had a powerful enough telescope and knew exactly where to look, you could find the sun's own light, reflected from the surface of Pluto, traveling back inward. Light that left the sun, traveled out to the edge of the solar system, bounced off that small icy heart and began its journey back, faint beyond description, barely distinguishable from the dark. But there, everything in the universe is in conversation. Everything is sending and receiving. Light, gravity, radiation. The universe is not silent. It is speaking constantly, in frequencies we are only beginning to learn to hear. You don't have to hear it all tonight. You don't have to understand it. You only have to rest in the knowledge that it is happening, that while you sleep, the universe will continue its ancient and patient work. Stars will form in distant nebulae. Planets will turn. Comets will make their long, slow approaches to the warmth of distant suns. Black holes will slowly, imperceptibly release their energy into the void. Galaxies will drift toward each other across millions of light years, drawn by the invisible thread of gravity on their way to a merger that will happen long after every human being who has ever lived is gone. And through all of it, through all those billions of years and billions of light years, Pluto will orbit, small and cold and beautiful, carrying its heart of frozen nitrogen, accompanied by Charon, that faithful companion, so close and so large that they pull at each other in an eternal slow dance, orbiting once every 248 years, patient, unhurried, exactly what it is, regardless of what we call it. There is a lesson in that patience, a gentleness in it. The universe does not rush. The universe does not worry about being categorized or understood or appreciated. It simply continues. And in that continuation, in that vast, unhurried, faithful continuation, there is something that feels, if you let it, like a kind of peace. Let your body sink a little deeper now. Feel the support beneath you, the mattress, the floor, the earth itself, all the way down through layers of rock and mantle and liquid iron to the solid inner core spinning at the center of the planet. You are supported from below by 6,000 kilometers of Earth. You are held. There is nowhere to fall. Above you, beyond the ceiling, beyond the clouds, beyond the atmosphere, the sky opens into space, and space goes on, and on, and on. Past the moon, past Mars, past Jupiter and Saturn and Uranus and Neptune, past Pluto and the Kuiper Belt and the Oort cloud, past Proxima Centauri and all the other stars of the Milky Way, past the Andromeda Galaxy and the other members of the local group, past the Virgo supercluster and the Laniakea supercluster and all the other vast structures of the cosmic web, all the way to the edge of the observable universe, 46 billion light-years away in every direction, where the light from the Big Bang itself is still arriving, still completing its 13.8 billion-year journey. And at the center of all of that, or rather, at one small warm point within all of that, is you. Breathing, resting, drifting. You are the universe, looking at itself. That is not a poetic exaggeration. It is a scientific description. The atoms in your brain, arranged by evolution and experience into the particular pattern that is you, are capable of perceiving and reflecting on the universe those atoms are part of. The universe has, through the long, slow process of stellar evolution and planetary formation and biological evolution, produced a structure that can ask where it came from. That is one of the most remarkable things about this particular moment in cosmic history. Not because humans are the purpose of the universe, there is no evidence of that, but because awareness, wherever it arises, is the universe becoming briefly, beautifully conscious of itself. And right now, that awareness is softening. The questions are quieting. The thoughts are growing slower and gentler, like ripples on a pond after a stone has sunk. The surface of your mind is growing still. And beneath that stillness is rest. Deep, dark, warm, ancient rest. Sleep is its own kind of space travel. When you close your eyes and let go, you travel somewhere that no telescope can follow. Inward into the private universe of the dreaming mind. Scientists don't fully understand sleep. They know it is essential. Without it, the body and mind begin to fail within days. They know it is ancient. Every animal with a complex nervous system sleeps, suggesting that sleep evolved very early in the history of animal life. They know that during sleep, the brain consolidates memories, clears metabolic waste, repairs tissues, regulates hormones, processes emotions. But the full picture remains in many ways mysterious, like dark matter, like dark energy, like the interior of a black hole, essential, present, powerful, and not yet fully known. And dreams, those vivid, strange, sometimes beautiful journeys the mind takes while the body rests, remain one of the deepest mysteries of neuroscience. We don't fully know why we dream. We don't fully know what dreams are for. But we know they happen. We know that somewhere in the dark of a sleeping mind, something is moving. Images forming and dissolving, emotions rising and passing, stories unfolding without a storyteller. The dreaming mind is doing something ancient and necessary, and often something wonderful. Perhaps tonight you will dream of space, of vast dark distances and slow wheeling stars, and the small pale light of Pluto drifting in the outer dark. Perhaps you will dream of something else entirely, something personal and warm and close. Whatever comes, let it come. You don't need to guide it. The dreaming mind knows the way. And if you wake in the night, as we sometimes do, surfacing briefly from sleep before sinking back, remember this: above you, the stars are still there. Above the ceiling and the clouds and the atmosphere, the universe is continuing its slow, faithful work. Pluto is in its orbit. The Milky Way is turning. The cosmic microwave background is still faintly humming in every direction, the echo of the first light, the oldest sound. Everything is as it should be. Everything is held. You can close your eyes again. You can go back. The night is long and soft and full of quiet. Rest now. There is nothing to do. There is nowhere to go. There is only this breath and the next one and the slow, gentle slide into the warmth of sleep. You've traveled a long way tonight, from Pluto to the edge of the universe, from the birth of stars to the slow cooling of the cosmos, from the Big Bang to this moment, here, now, in the small and precious warmth of wherever you are. That's enough. That's more than enough. Sleep well, dear friend. Sleep gently and deeply and fully. Let the stars watch over you tonight, and they will, as they always have, burning their patient ancient fire in the dark above the clouds, above the atmosphere, above the world. They don't need anything from you. They just shine. And tomorrow, or the day after, or whenever you're ready, we'll be here, with more stories, more journeys, more long and quiet nights among the stars. Good night, sweet dreams, and wherever you are in this vast and beautiful universe, you are not alone. The cosmos holds you as it has always held you, as it will always hold you. In the spin of the earth, in the warmth of the sun, in the slow turning of the galaxy, you are home, and it is time to sleep. Good night.